Welcome protein coders, let's build some coding muscles. Today we're gonna learn about segment tree. What is a segment tree? You can say it's a data structure, a binary tree, in fact a balanced binary tree, which we use to query the intervals or ranges. We use this when we have to find or query multiple queries such as finding maximum between the index 1 and 6, then finding maximum between 2 and 4, or it can be the sum also. Like we are querying the array again and again and again. Okay, we have a lot of queries, and the time complexity for this will of course shoot up, right? Because for every query we're gonna traverse the array. So in such cases we use the segment tree. Okay, for efficient range querying and updations. Let's see how to build a segment tree. Here let's take an example of range sum query. Okay, we'll build segment tree based on range sum. Okay, let's make a node and it will represent the sum of index between 0 to 4 of vector, which is 14. Okay, sum of all the nodes. Then we will make two nodes out of it and we will divide the indices from mid. Okay, from 0 to 2 and 3 to 4. Okay, mid will be 0 plus 4 by 2. So the sum from 0 to 2 index is 8 and 3 to 4 is 6. Similarly 0 to 2 will be divided in 0 to 1 because mid will be 0 plus 2 by 2 is 1. So 0 to 1 and it will be 2 comma 2, right? Yeah, so 0 to 1 will be 7 and 2 comma 2 will be 1. Similarly 3 to 4 also. 3 to 3 will be 4 and 4 comma 4, this node will have sum 2. Similarly 0 comma 1 will also get divided into 0 comma 0 and 1 comma 1. And if you see carefully, the leaf nodes are the elements of the vector, and this is a balanced binary tree. And for the size of the segment tree, we approximately take it as 4 times the number of the elements present in the vector. Okay, yeah, it's your homework, you have to study why we take it as 4n. Okay, it's simple observation. Okay, using geometric progression, and also you can find it using, like, we have n nodes and the internal total nodes will be n minus 1, so it's approximately 2n, but we take 4n for safe allocations. Okay, just for safety purposes. So let's build our segment tree here, which having size as approximately 4n. Okay, let's index it. I will be the index of the segment tree. We are representing the segment tree in form of the array. Okay, and let's take L and R also. They will represent the starting and the ending index of the vector. So root node will contain the sum of all the elements, and the children will be from L to mid and mid to R. Now in array representation of segment tree, if we have a node at index I, then its left child will be at node 2i plus 1 and its right child will be at index 2i plus 2. Just simple array representation of the tree. Okay, now let's see. The first node will be, the root node will be the index number 0. Okay, so let's fill it in our segment tree. Then the left child will be 2i plus 1, which is 2 into 0 plus 1, which is at index 1. Okay, so and the next node will be I equals to 2, right? Similarly this node will be 2 into I is here 1. Okay, 2 into 1 plus 1, 2 into 1 plus 2, 2 into 2 plus 1, 2 into 2 plus 2, right? So similarly we will fill our segment tree vector. Now let's see it in more detail and let's have a dry run properly with the code. So we have our function here, okay, void build tree, which has first element as I. I is the index of the segment tree, and L and R are the starting and the ending pointers of the vector, the input vector. Okay, so first thing we will do is finding the mid, which is L plus R by 2, and let's make our initial node of our segment tree 0 comma 0 comma 4, which is I, L and R. Okay, now what we do is we use recursion. You can say recursion leap of faith here. We will say, hey, I build the first node. Okay, now go to the left and build the left subtree. Go to the right and build the right subtree. You will see in a minute how we're gonna update the segment tree. Okay, just right now think about the building the segment tree. First I am saying, hey, go to the left child which is at index 2 into I plus 1 and have the L comma mid part of the vector and build the left subtree. Similarly the right subtree. So let's build it. So first we will go left and left, right. So left node, left child will be at index 2i plus 1 where I is the previous I. Okay, 2 into 0 plus 1. So 1 comma L comma mid, 1 comma 0 comma 2 is the mid. Okay, similarly it will also call the left child, right, 2 into 1 plus 1 comma 0 comma 1. Similarly this will also call its left child and make a node. Now here you see the L is equals to R, so we will come back. This is our edge case. Okay, and then we will go to the right side and we'll make right node 1 comma 1. So let's write our edge case also. If L equals to R, then we will mark the tree of I equals to L, or you can mark it as R also and return. So let's mark them. They are now the leaf nodes. Okay, so let's mark them. So 0 comma 0 sum and 1 comma 1 sum will be nothing but the elements of the vector at index 0 and 1, and we can also push them into the segment tree, right? They will be at index 7 and 8. Let's fill them into the segment tree also. Now while returning, I can update the sum of the parent node, right? How can I update this? I can write the segment tree sum at index I is equals to the sum of both of its children's. So when the recursion will go back, I can update the sum of the node at index 3, right? It will be 5 plus 2 7, and let's mark it in our segment tree also. At index 3 we'll mark it as 7. In similar fashion, let's build a segment tree. Okay, now our recursion will go back and it will call for the right node, right? It will get the index and LNR, right, because it's a leaf node. We'll mark it, and while returning back we will store the sum, right? And whenever we are filling a node, we are marking it in a segment tree vector also. Let's fill the segment tree a little bit faster. Okay, so now recursion will go back and call for the right side of the root node, and the similar steps will follow. Whenever we reach a leaf node, we will update the element, right? And whenever we are returning, we are getting the sum of those children nodes. So let's revise what we have studied today. We studied about segment tree, right? They are balanced binary trees used for efficient querying and updating, right? When we have to do range queries again and again. So in those cases we use segment tree. And we saw for the safer allocation, we take size of the segment tree as 4 times the number of elements in the input vector. Okay, and we also learned that we will represent the segment tree in the form of the vector, where for every index I, its left child will be at index 2i plus 1 and right child will be at index 2i plus 2. Then we saw the code for it, right? First we will find the mid, then we believe in recursion and use recursion to build the left subtree and the right subtree, and while returning back we are just adding the values of the left subtree and right subtree. And we have an edge case. Whenever the L is equals to R for the leaf nodes, we will just write the elements of the input vector, right? And while returning, we will just add them, aggregate them. Okay, and the size of the segment tree here is approximately 4n, right? And where n is the number of inputs of the vector. So that's all from my side, guys. If you have any questions, please mention them into the comment box. Hope this helps. Keep practicing, keep smiling. Thank you.